Hi, I'm Dirk Philip, a PhD student in the Seismology and Wave Physics group at ETH Zurich. In this online presentation, I will be showing an evolutionary full-waveform inversion of the African plate. Although I am the one presenting, the contributions of my co-authors have been vital to make this work possible. I will start with the motivation for this work. This figure shows the size and makeup of the IRIS-DMC database, the largest database of seismic data on Earth. As can be seen, the amount of data is growing rapidly and it roughly doubles every 3 to 5 years. This new data can be used to better constrain and update our Earth models. With travel time tomography, performing this update is quite straightforward. One can simply occasionally rerun an inversion with the expanded dataset. This is possible because travel time inversions are relatively cheap and fast to perform. For full waveform inversions, however, this would result in a large computational burden, and restarting an inversion is not feasible. We therefore need to design our method such that the ability to efficiently incorporate new data is part of its design. To mitigate these challenges, we present an evolutionary full waveform inversion. The approach does not require any inversion restarts. The dataset can be expanded without increasing the iteration cost or interrupting the optimization. It is built with the same principles as the dynamic minibatch method, which I presented here last year. For the people who haven't seen this, I will quickly recap the most important aspects of it. The dynamic minibatch approach is similar to stochastic gradient approaches. In contrast to regular methods, we define the misfit function as a sample average of all sources. We can now approximate this misfit and its gradient with a smaller subset of these sources from a so-called minibatch. There are two main challenges with stochastic gradient descent methods. How do we know if the minibatch gradient still gives a good approximation of the larger dataset's gradient? This is important to know, as poor approximations are associated with poor convergence speeds. And how do we know if we can accept a model update if different data is used in each iteration? To mitigate these two problems, we introduce a control group. This is a subset from the last iteration's minibatch and seeks to approximate its gradient within a set angular tolerance. How this approximation works is something I will get back to in a moment. The quality of the control group approximation then works as a proxy for the quality of the minibatch gradient's approximation of the full dataset. If many sources are needed to approximate the minibatch, it means each source contains significant information and we dynamically grow the next minibatch size or vice versa. In addition, it enables a misfit comparison between subsequent iterations, and this informs us whether we can accept the updated model. In the previous slide, I mentioned how the minibatch gradient is approximated by the control group. This figure shows an example of a gradient computed for 125 sources, indicated by the yellow circles. Red colors represent areas where the model should get faster, and blue colors represent areas where the model should become slower to reduce misfit. To approximate the gradient, we use the following algorithm. First, we remove one gradient or source from this batch of gradients. We then measure the angle between this reduced gradient and the to be approximated full gradient. We then try this for all possible sources and then remove the source that results in the smallest angular difference and continue to do this until a certain threshold is met. This plot shows how the gradient deviates as a function of the number of sources. With all sources, we of course get no deviation, and with about 20 sources we can approximate the gradient of 125 sources to within 20 degrees. To give an idea how this looks like visually, I will now show several approximations of varying quality. On the left side you can see the full gradient. On the right side you can see the approximation with a single source. With one source we can already capture the strong increase that is needed in the Mediterranean region. With 10 sources there is already considerable similarity between the two gradients, and with 40 sources both gradients start to look extremely similar. It is important to realize that all of the gradient approximations that I showed lie within 90 degrees of the full gradient and would thus be able to guide us in the descent direction. In essence, this component of the dynamic minibatch approach can be seen as a form of optimal experimental design. The algorithm automatically learns which and how many sources are required to make good updates. To show how this works, we try to achieve the synthetic target model starting from a 1D model. This is the recovery of a conventional full waveform inversion that uses all data in each iteration. As can be seen, we have good recovery in the entire region that was surrounded by sources. This is the recovery using the dynamic minibatch approach. They are basically the same, with one major difference. Over 5,000 simulations were required for the standard approach, while only 1,500 simulations were required for the dynamic minibatch approach. The following curve shows how the models converge as a function of simulation cost. The y-axis shows the L2 misfit of the model parameters, and the x-axis shows the number of simulations that were required to obtain a model. A model of similar quality is recovered as roughly 25% of the cost in this example. Larger speedups are expected for larger datasets, as a good gradient approximation might be possible with relatively fewer sources. To summarize, the method leads to significant computational savings. The dataset can easily be expanded during the inversion, since we can just expand the complete dataset from which we sample the events. Iteration costs no longer scale with the size of the dataset, thereby enabling the use of massive datasets in full waveform inversion. If you want to learn more about the dynamic minibatch approach, you can scan the QR code to find the paper. I also recommend watching the presentation by Sylvie Thrastarsson in this session. He uses the same principles in addition to smart meshing techniques to greatly speed up a global full waveform inversion. These previous developments enable a mode of inversion that we refer to as evolutionary full waveform inversion. To illustrate how this works, we show an example where we start from a 1D Earth model and the limited dataset of roughly 1,500 source-receiver pairs that was recorded in the early 90s. With this small dataset, it would have been difficult to obtain a model that shows any meaningful features. Within a single inversion, we will gradually expand this dataset and converge to a more detailed model that is constrained by a much larger and contemporary dataset. I will now play a movie that shows how the model evolves over the course of many minibatch iterations. The right-hand side shows a spherical slice through the VSV model at 100 km depth, and the minibatch data coverage is shown on the left. The use time range of the data and the iteration number is shown at the top. As you can see, as the dataset expands and data recorded by more recent station networks is incorporated, the model starts to show more and more refined structure. For example, the West African craton and slow zones beneath the East African rift system. In this example, we have kept the regularization constant to isolate the effects that the addition of new data has on this inversion, but in principle it's possible to adjust this to the size of the dataset, for example. To summarize, we have shown that the dynamic minibatch approach can be used to implement evolutionary full waveform inversion. The main benefits are that one can start with a simple model and dataset and progressively update the model as new data becomes available. Prior data can be kept in the inversion without increasing the iteration cost, and no restarts are necessary. If you would like to learn more about this approach, you can find more information in the paper that can be accessed by scanning the QR code. The previous example was made to illustrate the utility of evolutionary FWI. We will now show a full-scale example that starts from current times. The starting model is the collaborative seismic Earth model. This time we will go down to a period of 30 seconds, rather than the previously used 70 seconds in the toy example. The complete dataset consists of almost 400 earthquakes and 185,000 unique source-receiver pairs. This movie will show how this VSV structure is recovered over the course of many iterations. You can see how areas like the FR triple junction are becoming well defined as the inversion progresses. In addition, you see several other anomalies popping up. We will now show several depth slices through the latest model. On the left-hand side, you see the initial model, and on the right-hand side, you see the latest model. It is particularly nice in this example to look at the area of the East African rift system. Here you see the red hot anomalies slowly going downwards towards Tanzania. The color map gets rescaled. Here you see quite strong anomalies again under Tanzania. We will now take a bit of a closer look at the final model. The left figure here shows the topography of the African continent, with the location of volcanoes indicated by red triangles. The right figure shows our latest model at 70 km depth. In Africa, there are several regions with significant topography, even though there are no nearby plate boundaries. The origin of these anomalies are believed to be related to hot material coming from the mantle. If our model and this theory is correct, we would expect to see slow velocities beneath these areas with dynamic topography. If we zoom in now, we can indeed see slow anomalies right beneath mountain regions like Tibesti and Hugar. We also see a line of slow anomalies that aligns very well with the Cameroon volcanic line. Another dominant feature is the Afar triple junction. Here, 3 plates are rifting apart. This area is considered a present-day example of continental rifting leading to seafloor spreading. This is a cross-sectional plot through the East African rift system showing our initial model. If we take a look at the final model now, one can see low velocity anomalies deep beneath the Afar region and Tanzania. To conclude, we have shown how the dynamic minibatch approach enables evolutionary FWI. Evolutionary FWI enables efficient model updating since restarts are not necessary and data can simply be added to the inversion. We have applied this method to obtain a new and detailed tomographic model of Africa. The model is constrained by a larger dataset than previously feasible as a result of the dynamic minibatch innovation. Finally, I would like to acknowledge the waveform solver Salvis. All of the forward and agile modeling was performed with it. If you want to learn more about the solver, you can contact Michael Afanasyev. Thank you for your attention. Let me know if you have any questions. You might be able to reach me through the session, and otherwise you can always send me an email.